Okay, this is a video solution for problem 14 on the momentum test review. It says that a ballistic slab, a 0.1 kilogram bullet, is fired vertically into a 5 kilogram block of wood. The bullet embeds itself in the block of wood, and after the bullet is shot into the block of wood, the block and the bullet rise 4 meters off the ground. Determine the speed of the bullet before it strikes the wood block. Okay, so again, a big key to this is just being able to figure out what's going on. So I know that I have a bullet that's moving and it's going to strike this block of wood. Nobody asked you anything about what's going on with the bullet while it's rising up like this. Okay, we don't ask you how quickly it's gaining or losing speed as it's traveling here. So you don't have to worry about gravity there. All you care about is how fast is it going at the instant it collides with the wood. How fast does it need to be going in order to embed itself in the wood and drive that block of wood up to this height? Okay, up 4 meters. That's all that's going on. So those of you who got stuck going, well, I didn't know how to handle the impulse delivered to the bullet while it was traveling towards the block of wood, you don't need to worry about that. You were making this problem harder than it is. Okay, so what we ultimately want to figure out is how fast this speed is, how fast the bullet is going beforehand. Well, the answer to that really comes from way back over here when we're looking at this bullet rising all the way up to that highest point. This is where we have the most information. So what I did was I kind of broke this up into 3 pictures. I labeled them 1, 2, and 3, before the collision, after the collision, and then at the highest point. And I started analyzing this from a gang of 5 perspective. So I said that my final velocity squared equals my original velocity squared plus 2 times acceleration times my change in position. I called it delta x. You really could have called it delta y because we're rising vertically. It doesn't matter really, as long as you know that delta whatever is how high you're rising. Okay, well, what other things do I know? Well, I know at my highest point, this thing has slowed. At its highest point, its velocity is 0. Okay, I know that my acceleration as this thing is rising is going to be the acceleration due to gravity. So g equals 10 meters per second squared directed down. Why do I know that? Well, if I drew a free body diagram for this thing, like I did here, the only force acting on it is the force of gravity acting downwards. If we're ignoring air resistance, which there's no mention of air resistance, so I think that's a safe assumption. Okay, and then, so I know my velocity, I know my acceleration, I know also my change in y. So what I'm going to do is I'm going to solve this equation for the original velocity of the bullet and block right after they collided. So really for this spot. So when I go ahead and solved for original velocity, I plugged in my values, and I get that the original velocity of the bullet and block together, so kind of right there, right after the collision took place, which is my velocity at location 2, comes out to 8.94 meters per second directed upwards. Okay, and that's v prime, so v after of the bullet and wood right after the collision. So I'm going to take that over and use it now as I look at what happens between situation 1, or instant 1, when the bullet's still traveling towards the block, and situation 2, which is immediately after the collision. I know that in that collision, the only forces applied are bullet on block and block on bullet, or bullet on wood and wood on bullet. The W subscript was supposed to be for wood. So I know that momentum is conserved in that system. And again, I think it's useful sometimes to just highlight what your system is. So let's highlight what our system is. Our system is these 2 objects, the block of wood and the bullet. Okay, and that's still our system here. And the only forces acting on this from the instant right before to the instant right after the collision would just be internal forces, bullet on wood, wood on bullet. I know that gravity is going to exert an impulse afterwards. I'm not worried about that. I'm worried about the instant right before to right after. So I can say, well, momentum before the collision, which is everything, it's just all bullet momentum, mass of bullet times velocity of the bullet, equals momentum of bullet and wood afterwards. So that's why I have mass of bullet plus wood times v afterwards. I just solved for this v afterwards. I just solved for that. That's what I was finding over here. Okay, I indicated this is the velocity of the bullet and wood right after the collision. So it's just a matter of doing algebra from there. I divide by the mass of the bullet, and I get that the velocity of the bullet equals the sum of the masses times velocity after, divided by mass of the bullet. I plug in my numbers, and it spits out that the velocity of the bullet is 456 meters per second. That's pretty much it.